All right. Thank you, Jonathan. And thank you for the opportunity to tell you a little bit about how challenging it can be to control a quantum computer. So while I present, please interrupt me whenever you have a question. It's better to get to it when the question is coming up than wait till the end. A bit about me. I am a postdoc at Princeton University. I have done my PhD at MIT, and before that, I was at ETH in Zurich. And my focus was always on experimental and theoretical quantum computing. Particularly, I've worked with solid-state quantum emitters and superconducting qubits. And now at Princeton University, I'm trying to focus on how to improve the controllability of quantum computers, in particular, how to scale up these protocols such that we can really realize these systems. So enough about myself. Let's get started. We have about 1 hour. So first, I'll talk a little bit about quantum computing in general before I then dive into the topic of control. So when we talk about quantum computing, or generally harnessing the physics of quantum mechanics, there is the general topic of quantum information processing. So anything that uses quantum mechanics to really deal with information on itself. And we can distinguish a few different classes in this genre of quantum information processing. For example, we can use quantum mechanics to do sensing. So to detect magnetic fields more efficiently or just with a better resolution. There is the option to use quantum mechanics to realize secure communication. You may have heard that, for example, as shown here, the Chinese teams have sent up a satellite to communicate, as shown here, actually between China and Austria, so quite the distance through these satellites. So, and that is being done through the specific protocols that allow you to communicate securely, meaning if someone would try to interfere with your communication channel, you would be able to tell. And lastly, there is the topic of computing, where you use the physics of quantum mechanics to do computation and solve specific problems with it. I will focus on computing today, in particular how to control, as I mentioned already, these quantum systems. When we talk about quantum computing, there are again a few sub areas that one can look at. So for example, there's gate-based computing, and that's the most equivalent to a classical computer, like the computer you may be using right now. So it uses specific operations and to compute something and process the information that way. There is quantum simulation that uses some sort of mix. It has some gate components, there's some control over it, but there's also a lot of just fundamental physics to process information that it's behind it. So one just lets systems evolve by themselves. And lastly, there's really just annealing, which at this point is, if as realized so far, unclear if it's just a slightly better form of classical computing, or if there is indeed an advantage to it, a significant advantage to it. So again, one can distinguish here between like completely digital when it's gate-based, or almost analog when we move towards annealing. And I'll be focusing on the digital elements, so we're really controlling the system matters. Now, what can we use these quantum computers even for? Quantum computers are typically believed to be particularly effective in terms of quantum simulation. So really where there is something governed by quantum mechanics, a quantum computer speaking this language naturally should be able to provide you with an advantage. So that matters, for example, in chemistry, material science, or even physics. It has been shown that it can even be used in cryptography. For example, to some extent, some bank accounts still use, or banks use, the so-called RSA encoding and that is based on prime factoring. And Shor has found an algorithm using quantum computers that can do this significantly more efficient. And once we have such a quantum computer, we could really decrypt these codes very quickly and effectively break bank accounts. And it's also believed that quantum computers can be helpful in certain tasks, in particular optimization, for example, used in machine learning or artificial intelligence. To give you a bit of a better idea in a particular example, I want to focus on nitrogen fixation. That's a method to produce ammonia. Ammonia, as you may know, is very important to fertilization and therefore the production of food. So this particular enzyme or a molecule that you see here is responsible for the ammonia production in a specific bacteria that we know of. However, the way we currently produce ammonia is through the Haber-Bosch process, and it uses more than 1% of the global energy. It requires a high temperature and pressure to be produced, and that's the reason why it requires so much energy. However, the molecule that I'm showing you there is part of a bacteria enzyme, and it produces the ammonia in under regular conditions without this insane amount of energy. So if we could decrypt this molecule, we could actually figure out how to produce ammonia more efficiently. And so it's believed that this could be one of the first useful applications of quantum computers to really figure out what is going on in this molecule. And we can't do this currently with any classical computer to the extent that we really could figure out what's going on. But a quantum computer promises us that we could. Give you another example, I already talked about it a little bit. So Shor's algorithm, the base of these RSA codes is prime numbers. Now to the top, you see 2 prime numbers, and it's easy to calculate the sum. So when you multiply them, the result, right? And you see the result to the lower right. That's an easy task. Reversing this task, that's when it gets more complicated. If I give you a big number, tell me the 2 prime factors. That's a complicated task, and this difficulty is the reason why these RSA codes are relatively secure. So these RSA public key encryptions, it's depending really on very, very, very large numbers and 2 prime numbers. And so to the top right, I'm showing you now how long it takes for a classical computer in orange to calculate these prime factors, depending on how many number of digits your number has, and compare this to a quantum computer. In gray, you see how long it would take to calculate the numbers shown to the top left and bottom right. And you may see already the quantum computer can do this roughly twice as fast. And so if we increase these numbers even further, the quantum computer has a significant advantage, in fact, an exponential advantage. Today's codes, they use about 617 digits. That's about 2048 bits. And so if we do, again, this comparison, we see that the quantum computer requires about twice as long, more or less, relative to calculating the prime factors of this 10-digit number shown to the upper left, whereas the classical system would require about 2,700 years to do that. And that's why these codes are safe. To actually calculate such a number, it required the top 10 supercomputers and even more university clusters to really get this number figured out. And that's just a 250-digit number. And as I mentioned, today we use 670-digit numbers. So we even using several supercomputers, we cannot reach and figure out the prime numbers of today's factors. So with the applications now discussed and roughly what a quantum computer is promised to do, I will first discuss a bit more the fundamentals of a quantum computer. In particular, I will talk about it from a classical point of view and compare it with the quantum system. And then I will talk about the challenges that we face today, in particular, this control aspect that I've already brought up. So let me start with the fundamentals. So classically, you may be familiar with bits. So binary digit or short bit, it's either a 0 or a 1. And the state integrity, I'm saying it's an infinite because typically you encode this in a physical system. So it's either 0 volts or 5 volts. And the state integrity is infinite because even if it have something that is a volt, it's still considered a 0. Or if it is a 4 volt, it's at 4 volt, it's still a 1. So there is the uncertainty does not really affect you much. And so you don't have to correct for errors really. A quantum system, on the other hand, so quantum bits or qubits, that's a bit of a different story. So first, the states are superpositions. So a superposition can be pictured on this block sphere that I'm showing to the right. On the top, the north pole would now be your a 0 bit. So that'd be classical. And then the south pole, you would have a 1. So those would be your classical bits. However, a quantum bit can be in a superposition of those two states. And it's shown with this red arrow and this sum of the 1 and 0 with these amplitudes alpha and beta. Here, the state integrity is not guaranteed because you're kind of in between. You don't have this forgiveness and its uncertainty. And the state integrity depends on the lifetime of this system. So how long a state is constant. And roughly for systems that are not too affected by noise, typically the coherence time is about twice the lifetime. And the coherence time gives you an idea how many, it gives you a time window during which you can do computations. And lastly, the implementation of it in the physical sense is typically in a ground and excited state of a quantum 2-level system. That'd be the ideal qubit. So to summarize this, qubits are really noisy quantum 2-level systems, and they don't have the stability and forgiveness that you are familiar with a bit. If we compare this even further and actually see what we can do in terms of computation, we have on one hand the classical computers with these bits, the quantum computer with the qubits. There a question? Okay, so the classical bit, we have these discrete states, right? And the qubit, we have the superposition states, as already introduced on the previous slide. Now, if we start computing, say we have n bits, then for each, we have a function that we're trying to evaluate. Each bit combination needs to have one computation to run to evaluate the function. So for a 2-bit system, we'd have to do 4 function runs to evaluate all outcomes. If we use a quantum computer, we can do this in a single one. We can generate a superposition of all different combinations, run one computation, and then get the function output. So that's already hinting where the advantage is coming from. So this is so-called quantum parallelism. And the effect that you use here is quantum interference to then identify which of those functions is the closest to your desired result. The measurement again differs between a classical system and a quantum system. In a measurement of a classical system, it's deterministic. If your transistor is in the 0 state, you'll measure a 0. If it's in the 1, you measure a 1. If you have a quantum bit, qubit, that's probabilistic. So in these superposition states, you have a certain probability that it will be 0 and a certain probability that it will be 1. If you have a superposition as shown in to the left, so alpha and beta, then your probability to measure 0 is alpha squared, or the absolute value of it squared, and it'd be beta squared, the absolute value of it, to measure 1. So it's important to note quantum computers encode and process information fundamentally different than classical computers do. The process or the computation itself is based on gates, as it is for classical computers. However, the gates differ a little bit. Typically, you have gates that are interacting or acting just on a single qubit, and then you have gates that act on 2 qubits. So they generate an interaction between two. In terms of single qubit gates, you've seen the Bloch sphere, and what you do is you rotate the arrow arbitrarily on this sphere. And then the 2 qubit gates are these interactions, conditional interactions between two. If you pick now a few of these different gates, you can generate a set of gates. And if you do this in a smart way, you can generate a universal gate set. A universal gate set allows you to implement any algorithm that you desire. It doesn't say anything about how efficiently you could implement this algorithm, but it allows you to generate any arbitrary algorithm. One of those universal gate sets is, for example, shown here, with a Hadamard gate, an ST, and a controlled NOT gate. But then once you have defined such a gate set, you have to decompose it in hardware-specific native gates. Not every quantum computer platform allows you to equally efficiently implement these gates. Some of these gates cannot even be directly implemented as shown here. You have to tweak your gates a little bit to achieve the gate you want for your universal gate set. But the point is, you have some single qubit gates, some 2 qubit gates. You want to have a universal gate set. At this point, you're ready. Your quantum system is ready to implement an algorithm. Now with this, let's say we have now everything in place. We have a universal gate set and everything. Let's see where we are today. What have we experimentally implemented? And probably the most important milestone achieved lately is quantum supremacy. You may have heard of it. What quantum supremacy means is it is a time, at this point in time, when quantum supremacy is achieved, a quantum computer has done a computation significantly more efficiently than a classical computer can. Meaning it could be something like a quantum computer does something in a minute, the classical system would require a human lifetime long. So that's a moment in time, and that was achieved 2019 by the Google team. So Google used a superconducting quantum system. They called it Sycamore, which is shown to the right. All the crosses are qubits, and the blue parts are couplers that connect qubits with each other. So it's a 2D grid. One of the qubits did not work well, so they had only 53 that they could actually use. And with this design, which is then shown in an actual picture to the lower right, they were able to demonstrate quantum supremacy. So they did use an algorithm, so-called quantum circuit sampling, and they were able to do this significantly faster than supercomputers could at that point in time. So what they did is they engineered or achieved about 1,016 different states. They had to do over 1,000 single qubit gates and over 400 2 qubit gates. And at the end of each computation, there is a single qubit measurement. To run this algorithm, it took them 200 seconds on the quantum device. And at that time, they estimated it would take 10,000 years to do the same on Summit. That was at that time, the world's fastest supercomputer. However, a few days later, IBM pointed out that one could do this actually in 2.5 days. So on a classic system. And nowadays, so a few years after it was demonstrated, there are new classical algorithms that promise that you could do this even more efficiently, to the extent that the advantage of the superconducting quantum system shown to the right is no longer as significant. However, 2019, when this was done, it was indeed faster than the classical systems and the classical known algorithms at the time. So in that sense, quantum supremacy was achieved. Now, if we put this in a historic context, yeah?
I believe there was a question asked a few slides ago in the chat room. So someone asked, does it take just one computation for any number of bits for a quantum computer, or is that just for n equals 2 bits?
Which slide is that referring to? Now
I believe, go back. Back again. I believe it's this slide.
And the question is?
The question is in the chat room. So he asked, does it take just one computation for any number of bits for a quantum computer, or is that just for n equals 2 bits?
Ah, okay. It depends. So normally, what I haven't said here is that you can't just do one run. It's actually many, but you encode it the same way. So you run the circuit the same way. So in that sense, for this particular example, yes, even if you'd have n qubits and n not equal to 2, you could encode it such that you have to just run one algorithm to answer that one question. But to identify these amplitudes, you have to run this circuit multiple times. But it's the same circuit. So that part would remain the same. But to identify this through this probabilistic measurement, you run it multiple times. I hope it's a bit, maybe a detail too much, but I wanted to give a correct answer here. I hope that helps. So let me put this all in a historic context. And in particular, let me compare it to classical electronic computing. And if we look at how our devices that we use nowadays developed, then we start in the early 20th century, in like 1905, they developed the vacuum tube. With that vacuum tube, it took about 40 years, then they built the first computer, like the first digital computer. And that was the electronic numerical integrator and computer. They shorted and abbreviated it to ENIAC. And so that was entirely based on these vacuum tubes that you see to the left. But then it didn't take too much longer. In 1947, they developed the transistor. So the transistor that we still use today, but of course not what you see in this image. We use a much smaller version of it. But with this transistor, then it took a few more years, and then they had the first transistor-based computer. They called it the TX0. And as you see in this picture, it filled a whole classroom. Then until we had the first integrated circuit, it was past 1970. Until 4004, had about 4,000 transistors, if I recall correct. But at this point, really integrated circuits, that started with Intel, started accelerating the whole classical computing business. And so shortly before 1990, we had already 1 million transistors. And then it continued, everything seemed to grow well. We were fully following this Moore's law that doubles the number of transistors every 2 years. And in between around 2005, we already had dual core systems, as some of you may still remember. And nowadays, we use about 10 to the 9 million transistors. So it took over 100 years to get from the vacuum tube to the transistor, and now to about 10 to the 9 transistors. So really quite the transition. Now, if we look at quantum computers, the idea itself is from the early 1990s and 1980s, 1981, 1982. Richard Feynman proposed to use quantum computers for problems that are inherently quantum mechanical. In fact, he wasn't the only one who noticed this, this opportunity at this time. There was also a scientist in the Soviet Union who realized the same thing independently. So, but at this point, really the idea was born. But it still took a bit of time. There were some initial algorithms that were developed, but nothing of real use that really sparked the interest. But then 1994, Shor's factoring algorithm popped up, and that really started the idea that we should really realize such a system. With the factoring, we had the first real application that seemed useful. A few years later, he even proposed, Peter Shor proposed quantum error correction codes. And at that point, we had tools to also correct for this noisiness that I already brought up of qubits. And so in around 2000, the platforms were able to demonstrate single qubits and multi-qubit systems. And this kept going well and well until 2019, where we had this moment of quantum supremacy with these 53 qubits. And since then, a lot of industry has popped up on the market and is trying to build up systems that can really be of use. Because at the point when quantum supremacy was demonstrated, the algorithm that was used or the results that were achieved are not yet useful. So we can't really use these systems yet, even though they are already more powerful than classical systems, but we don't have really the control over them yet to the extent that we can do arbitrary things with them. So it's important to notice here, we have so much history in classical computers until we reached this level today that we are so familiar with and use on a daily basis, this power of classical computers. But quantum computers are not that old yet. The idea is 1980, but then really we're only working on these systems for like the last 20 years from an experimental point of view. And also the history of classical computer teaches us just because we have some platforms that work well now doesn't mean they're going to be the platforms tomorrow. So take the example, the vacuum tube being the system until like 1947, then the transistor comes on the market and everything changes again. So the fundamentals, let me summarize this real quick here. So we've established that they promise us to solve some very important problems and can do specific things significantly more efficient, at times exponentially faster. We've established that quantum supremacy has happened in 2019, and a state-of-the-art quantum system was able to outperform classical systems on a very particular task, but unfortunately, this particular task is not yet of use, and no useful task has been found yet that we could implement with the current systems. So that's the next step. We need to go for some algorithms and improve our system so that they can really be of use and achieve something that we can use to improve anything in the world. And lastly, the quantum computing platforms, as we're dealing with them today, they may not be the platforms of tomorrow, as the classical computing situation teaches us. So let me stop here real quick and see if there are any questions.
Yeah, I had two questions about something that you mentioned earlier, but I felt they might have a longer answer, so I kept them for the end. The first one was about quantum annealing. So correct me if I'm wrong, but I believe you said that it doesn't give a significant advantage over current like conventional computation, right?
That's correct. If you have the currently implemented quantum annealing approaches, it's unclear to what extent they are beneficial. If you have adiabatic quantum annealing, which has not been implemented, that would be equivalent in power to general quantum computing. However, as I'm pointing out, right, what has been done so far, we don't know if it really is beneficial.
All right. And the other question I had was, so about Shor's algorithm and the fact that you can use a quantum computer to break RSA encryption. I was just wondering, is there any reason why, someone can't just, get up and do that right now? Considering
quantum computer?
algorithms there. Yeah.
So Shor's algorithm has been demonstrated with quantum algorithms for the number 15, for example, but not for large numbers. The quantum computers are not large enough. You would need thousands of qubits, maybe even 10,000 if your qubits are not good enough. So that's the reason we don't have quantum computers with that performance and that size yet to demonstrate Shor's algorithm competing with the numbers that we would need to decode today. But it has been demonstrated for small numbers.
Okay, so theoretically we could do it, in the future, but the limiting factor is I guess the nascency of quantum computing, right?
Correct. Yeah. So it's been demonstrated, but not in a useful way. That's really where we're at. Yeah.
Right. Thank you very much.
Yeah, of course. Thank you for the question.
Hey, could I ask? I'm curious about your perspective. You mentioned the timeline with classical computing, and some people make different comparisons with where quantum is at right now. Some people say that we're still in the vacuum tube era because we haven't really settled on a set transistor. There's a lot of good candidates, a lot of good stuff going on, but it's very noisy right now. One architect told me once that they didn't really think that we're at the integrated circuit stage yet, but we are running integrated circuits, albeit very noisily right now. So where would you say we compare with, like, say, integrated circuits, or where would you say we fall on that timeline right now with quantum computers?
I would say everything you said is probably kind of true. On one hand, we have some sort of integrated circuits, and but on the other hand, as you also pointed out, we are still working with several different platforms. And while there are some platforms that are leading in some aspects, there is not a clear front runner that is leading in every aspect. And I will actually dive into this in the second part of the talk. But yeah, I think it might not be as easy to really draw a direct parallel where we are. All we can do is learn from history, but we may not be able to pinpoint where we are with respect to that previous timeline, because also the situation is different. If you think just how many more scientists are alive now, how much more science or engineering is being done compared to 100 years ago, what I'm trying to say is that back then, the vacuum tube was on the market and maybe a few other approaches, but now we have so many more resources to look into so many more directions. And that's also makes it even more difficult. And the complexity is so much more higher to also do a very fair comparison between all these different platforms and make predictions. So everything you said is kind of true.
All right, thank you.
Any other questions? All right, then let me continue with the challenges. And here I will dive, as I already said, into some of the details of these platforms. I will start with the DiVincenzo criteria that lays out what a quantum computer really needs to be operational. So first, what we need is a scalable physical system. And the qubits need to be well characterizable. That's already where some of the current avenues are struggling with, meaning that it is scalable. Then once you have such a system, then you have the initialization. So you want to set up the problem. So you have to be able to manipulate the qubit states and do this with good control, fidelity. Then I already mentioned this concept of coherence times. You want to have a long coherence time, because the longer your coherence time and the faster your gates, the longer you can do or the more computations you can do. Then you want to have a universal set of quantum gates to do this computation, to implement arbitrary algorithms. And lastly, you need a way to measure out your qubits, so to get this solution out of your quantum system. If we now dive into what this means, like in terms of hardware, and compared to a classical computer again, so we have the classical computer being composed of a CPU that does the processing. We have a communication bus between it, between the CPU and your RAM, so the random access memory. We have this interconnect between processing and memory, and then through this bus, you're putting in information or reading out. The quantum system is not that different. You have the quantum processing unit, and that's where the major focus is on at this point. You have the quantum random access memory and the quantum link between those two. And then you would have a classical way to put information in and get information out. So the input and output in that sense would be same as in the classical system, classical. And it is envisioned that the quantum processing unit would have needs very efficient control, so you can do the computation as correct as possible with as few errors as possible. The quantum random access memory, on the other hand, requires a long-lived qubit so that you can store information for a long time. And at this point, it is believed that the quantum bus are probably going to be so-called flying qubits, which is nothing else but photons. So that's the general plan to build this whole quantum computer at the end. But again, the major focus has been on the quantum processing unit. And if we look at it again from a classical point of view and look at it, the software stack or the whole stack to control it, then we see that the quantum algorithm is now at the top. And then you have a lot of pieces in between that translate this quantum algorithm in something that the quantum computer can understand. And at the bottom, you see the quantum chip with all these qubits. And then the quantum to classical, this is where this control elements are happening. How do we interact with these qubits to efficiently implement these gates? And that's today's focus. If we think about more what those qubits are, then I'm showing you this graph here that gives you an idea what kinds of qubits there can be. So you need something that behaves quantum mechanically. That can be, for example, a photon, a nucleus, an electron, Cooper pairs, or something topological like a Majorana fermion. So I'm going to dive a bit more into what these systems can be composed of, but this gives you an idea what the very fundamental piece your qubit needs to be a qubit. So if we think about photons, you can have photonic quantum computing so that you can encode the information in the polarization or in the time. So you either have a photon at a specific time or you don't. So that's this 0 and 1 component. Then you can have the superposition element. So you may or may not have a photon. There is the approach to trap ions. And here you can encode information in the energy states. It can be the hyperfine or optical states. And you can have just typically it's ytterbium, barium, or calcium ions that are being used. You can also do this with neutral atoms. So you don't ionize these atoms. And then the physics changes a little bit and how they interact changes. There's the approach to use solid state defect quantum centers. Those are crystal defects in, for example, diamond or silicon carbide, solid state systems where you just really destroy the crystal structure in one specific point or add an impurity or something like this. Then you can have quantum dots that are grown and engineered systems. You can have these Majorana qubits. And it's important to point out here, while they're very promising as a theoretical concept, they have not been demonstrated yet. It's unclear if one can engineer that at this point. And lastly, there is the current, a strong current focus on these superconducting superconducting qubits as used in the quantum supremacy experiment by Google. And to put this in perspective again, we have with photons or ions, neutral atoms, very natural quantum systems. So they exist in nature and they're quantum mechanical. As we go down this list, we have artificial quantum systems. So those are systems that we engineer and have therefore control over their behavior to a large extent. Superconducting quantum systems are really, they don't exist naturally in nature. We can also distinguish now these natural quantum systems and what if they are in host materials or not. So if you take photons, they need to be in some material to be guided. Otherwise, you don't know where they are. You need to guide them from point A to point B. So that's what I'm saying. There's some host material. But the photons themselves, so the qubits can move from A to B. They're not always at point A. Whereas the solid state defects, quantum dots, Marana, and superconducting qubits, they'd be stable in a host material. Now, with this host materials, you get some advantages, but some disadvantages, as always. With the host materials, you are now surrounded by something that is most likely not perfect because you have some material around it. But on the other hand, you have something controlled again, which you don't have, for example, with neutral atoms or trapped ions. They are simply in vacuum. So those are the currently pursued platforms, I would say. And I'm going to dive a bit deeper into the photonic quantum system, trapped ions, and the superconducting quantum computing, and then tell you a bit more how all those systems here compare with each other. So the qubits themselves for a photonic system can be in a polarization, so it can be horizontal or vertical. The trapped ion is encoded in the electronic state, so either it's in a higher or lower energy state. And the superconducting system is encoded in these systems, in these superconducting loops that are separated by a little Josephson junction, which is simply an insulator in between two superconductors. And that gives you enough nonlinearity to engineer such circuits where you distinguish the states by, for example, the direction of the current flow. The way you control them now is, for example, for photons with interferometry. So you have such Mach center interferometers where you have these photons interfere with each other. And through that, you can, for example, engineer single qubit gates. Trapped ions, you often use lasers to get them from one energy state to the other. And for superconducting qubits, you use microwave signals. So the microwave signals would be in the frequency range of, for example, your Wi-Fi. So those are three systems that are currently quite promising platforms, and the way you could encode qubits in these quantum mechanical systems and the way you can control them. Now, if we compare all these platforms that I've shown you previously in terms of their size, because again here, if you think of the classical systems, the vacuum tube or also the early transistor, they filled an entire room, whereas now it's just a laptop or even a cell phone that contains significantly more transistors than the first classic computers did. So here, what I'm trying to say is size can matter in terms of scalability. And let's look at that a bit more carefully. So a nanometer, to give you a reference, that's the size of an atom. 10 nanometers, that's about a protein. The coronavirus is about 100 nanometers. Bacterium is about a micrometer. An animal cell, about 10. Human hair thickness, about 100 micrometers. And then a credit card thickness is the thickness of it, it's about a millimeter. So that's kind of like the scale that we're working with. And so these color centers, so these solid state systems or shallow donors are between an atom and a protein. Then we have quantum dots, which are often between about a protein and a coronavirus. Then we have neutral atoms, which are actually closer between a coronavirus and bacterium. then trapped ions and topological devices between a bacterium and an animal cell, and then transmos to superconducting systems that, again, Google used, they're actually, in fact, larger than the thickness of a human hair. So quite a significant spread. And so if you think about having to build thousands or 10,000s of these systems, you can imagine that probably a transmon system or superconducting system will take up quite some space. Whereas if you would go for the most left systems like semiconductor systems, that could be made quite compact. If we look at now more specifically about the control, then we compare again these systems from an ion trap, superconducting system, quantum dot, solid state system, so these color centers, or nuclear magnetic resonance, another platform that is known to not work, but it is a very good test bed. So the important point about this slightly confusing graph is that as you go up, your gates are slower and slower. As you go to the right, the gate performance gets better and better. So what you would want is to be in the lower right corner. That's when you're really good. So if we look at which systems are really good, then we see red stands out. The ion traps are really performing with high performance, but they are a bit slower. And then we see that the superconducting systems, they are very fast, but not quite as good as the trapped ions in performance, but again, so much faster. Now, as I already introduced, it's not good enough to just have a fast and good gate. It's also important how many gates can you apply. So this circuit depth or quantum volume is sometimes also a term that's being used. So how many operations can you do during the coherence time? And so here we see that superconducting qubits and quantum dots are on the lower end. Trapped ions are pretty long-lived, so you can do some computations over the range of up to a second. And then we have solid state or NMR systems, so these more like atom systems that are having very long coherence times, but they're also slow. So here you would want to be as high as possible. And so the summary here is the highest gate fidelity you can achieve with the trapped ions, so the red pieces to the very right. The fastest gates you can, at this point in time, achieve with superconducting qubits, and the highest coherence time with nuclei. But it's not sufficient to just have one to be extremely good. You need to have this ratio. And currently that's believed to be ion traps, where one could do the most computations during this computational window that's defined by the coherence time. So I was asked, which one is maybe the leader, which platform could be like the transistor, and which ones are maybe the platforms that may not succeed. So here it's already shown, ion traps are currently very good, but quantum supremacy has not been demonstrated with ion traps. It was used, superconducting qubits were used for it. So yeah, we're in a range where it's a bit unclear which platform will really succeed. So the general challenge is that all of these systems are affected by, especially when there's a host material, or noise sources in the material itself. I already mentioned there in materials, or noise, environmental noise. You can have interactions between the system, such as crosstalk or the tunability of their interaction. And to the right, you see the performance it gets for 2-qubit gates. It gets better and better, but as soon as more than 2 qubits are on your processor, the performance gets worse again. So there are some effects that have not been considered yet and need to be taken into account, such as crosstalk. So that's the point of this graph. It gets better and better, but now as we scale up, it gets worse again. And then the last part is the scalability. How do we scale these systems up? How do we add more and more qubits? And as we see for most systems, this is happening for superconducting qubits, for trapped ions, and so forth. But as we have more and more qubits, we also need more infrastructure to control them. And everything needs to scale accordingly. And lastly, once we have everything scaled up and operational, we also need to have it in some form that we can integrate it and package it, such as the integrated chip from Intel. So this is all things that all of the platforms still have to figure out. So I mentioned, well, my title is how to control this system. So I'll point out two particular tasks or problems, challenges that are limiting most platforms at this point. So what you see here are 25 qubits shown in this as block spheres. So say I would want to control the qubit in the very center with the red block vector, then I have interactions with the neighboring qubits. And as the block spheres fade, the interaction gets weaker and weaker. And this is at one point in time. But as you see, like each qubit does something and it experiences the environment a bit differently. So the qubits surrounding each qubit differ a bit, and the materials or the control, everything is slightly different. So each qubit has their own environment. Now this crosstalk can happen between the control signals. So you see to the very left, I'm sending in some control to steer qubits in one or the other direction. These signal lines are very close by to each other. So there can be signals jumping from one line to the other that is not supposed to be there. So I'm steering potentially the wrong qubit. So, or I could really just have crosstalk between qubits. So 2 qubit gates that I don't want to happen. So all these effects reduce the performance. And so therefore the result is not accurate. And for example, if I would want to apply just a simple rotation by 90 degrees of the center qubit, the center block vector as shown to the slightly left, then each of the qubits would experience also some slight shift, some slight rotation as shown here. And that's this error that we don't want, this crosstalk error. That's something as we now scale up the systems and add more and more qubit that we really have to figure out, how do we deal with this? And then the other important aspect is system parameter drift. These things are not constant in time. For example, the environment can be oscillating. So the qubit experiences a different environment at time t or at time t plus delta t. Then energy can be absorbed from outside or emitted to the external world. And that changes again how the environment interacts. For example, a radioactive burst changes the entire environment and the qubits behave differently after this and therefore the control with them. Furthermore, as a quantum processor ages, they also behave differently. And all this needs to be considered when we control these systems. So again, here at a time after I may have created the perfect 90-degree rotation, I'm again inducing some shifts that are not supposed to happen. So let me summarize these challenges. I believe at the moment, trapped ions and superconducting qubits are probably the most successful platforms and therefore the front runners. However, who knows how much longer? Because each platform can succeed in some aspect, has some promise in one way or the other, and could, if some key technology is being developed, overtake all the other platforms in a second. Lastly, most platforms really struggle with these control problems, such as when we scale things up, crosstalk and parameter drift, as well as integration challenges with due to these material defects start mattering as we add more and more qubits. And that limits us currently to really just go from 10 qubits to 1,000 qubits. So that is one of the main challenges we have to solve now. So let me summarize the entire talk before I ask if there are any questions. So we've seen that quantum computers can solve quite interesting problems, such as, for example, nitrogen fixation. quantum supremacy has been demonstrated with super and qubits. However, also trapped ions is a very promising platform. But who knows what platform will be the final one that we're going to build really useful quantum computers with. And that's the key message of my talk is that one of the bottlenecks that we are dealing with now is scaling these systems up and maintaining the controlled performance. And that's mostly reduced to the signal crosstalk and parameter drifts in time. So let me ask you at this point if there are any questions. If not, let me thank you for your attention. I appreciate you all staying up that late. And if you have any questions, feel free to send me an email or add me on LinkedIn, and I'll try to answer your questions as well as I can. Thank you.